All right, once again, we are here with some stoichiometry problems, and we're starting out with one that we should know how to do already. We start out with lead-2 chloride reacting with nitric acid to create lead-2 nitrate and hydrochloric acid. And what we want to know from this is if we have 58 moles of lead-2 nitrate, how many moles of HNO3 do we need to produce it? Okay, so we treat this just like any other conversion problem. We start with 58 moles of lead-2 nitrate. And now our job is to figure out what unit we want, what unit and compound. So I'm going to draw out my fraction, just like I do. And then I look back at the problem, and I figure out I want moles of HNO3. That's the one that I want. So that has to go on top. Mole HNO3. Okay? Then, what unit do I want to cancel? Well, I look back at what I'm given, and I recognize that I want to get rid of that. So I want to get rid of moles of lead-2 nitrate. Now, as for what numbers are going to go here, for that, I have to look back at my balanced equation. Okay, and I find each compound and figure out how many moles are given to me in the balanced equation. So for HNO3 is here. The coefficient before it is a 2. So that tells me that I have 2 moles of HNO3 for every 1 mole of lead-2 nitrate that's created. From there, I make sure that my units and compounds cancel, and I multiply and divide as normal. So 58 times 2 divided by 1 gives me 116 moles HNO3. And that's my answer, which is great and all, but moles can be a little bit difficult to try and measure. So oftentimes what we can do is something like number 2, where if I know the mass of one of the compounds, I can use it to find the moles. For this example, I am trying to combust 34 grams of methane. I need to know how many moles of carbon dioxide is produced. So I want to go from grams of methane into mole of CO2. Problem is, I can't do that. I don't know that conversion. However, what I can do is go from grams CH4 to moles of CH4. That's something I know how to do. And then from moles of CH4 up to mole CO2 using the same kind of thing we did before. So treating it like a conversion, I start with what I'm given, 34 grams of methane. And then what I need to know is how many grams of methane are in 1 mole of methane. Okay? For that, I would need the molar mass. And I just so happen to know that the molar mass of methane is 16.04 grams per mole. So that would cancel out my grams and leave me with moles. So I'm halfway there. I've now gone from grams into moles of CH4. Now I want to go from moles of CH4 to moles CO2. So how do I do that? Well, first I draw out my fraction. Then I know I want to cancel out mole CH4, and I want to get mole of CO2. Just like the problem before, I'm going to look back at my balanced chemical equation to try to find these coefficients. CO2 tells me that there is 1 mole of CO2 for every 1 mole of CH4. So it's at a 1-to-1 ratio, which is quite nice. So I multiply and divide as usual. 34 times 1 mole CH4 divided by 16.04 times 1 divided by 1. That gives me 2.12 moles of CO2. Very doable. But still not super useful, because if I wanted to know the mass of CO2, that is something that I can measure significantly easier. So oftentimes what we end up with is something like this. Given the reaction iron plus chlorine yields iron 3 chloride, what is the mass of iron needed to create 22 grams FeCl3? So here's what we got to do here. We know that we are starting with grams FeCl3. We want to eventually get to grams of iron. To get there, we have to use moles as an in-between, just like we would any other time. Now I can go from grams into moles, FeCl3, and then moles, FeCl3, to mole of iron. And then just like any other problem that I've done so far, I can convert moles into grams. So, starting with our 22 grams of iron 3 chloride, I want to convert this into mole FeCl3. I want to get rid of grams FeCl3. To do that, I need to know how many grams are in 1 mole of iron 3 chloride. That would be the molar mass, and I just so happen to know that that is 162.2 grams per mole. That cancels out grams of iron 3 chloride, moves me into moles iron 3 chloride. From there, I'm going to use the same thing that I've been doing through these whole 3 problems and use the molar ratio between iron 3 chloride and iron to convert my moles. Okay, so I want to go from mole iron 3 chloride to mole of iron. To do that, I find the balanced equation. Iron tells me that there are 2 moles for every 2 moles FeCl3. That works out pretty well for me. Moles cancels with moles of FeCl3, leaves me with moles of iron. But I don't want moles of iron. I want to get to grams of iron. So now I have to convert from mole Fe to grams of iron. Now, here's a very, very common mistake. What a lot of people want to do is they look at this and they think, oh, 2 moles here, that means 2 moles of iron have to go here. And we cannot do that. The reason being, we need to make sure that this whole fraction here is on its own. That fraction shouldn't depend on anything that we've done over here. What we need to know here is the number of grams in 1 mole of iron. We don't need to know the number of grams in 2 moles or 3 moles or whatever. We have to know the number of grams in 1 mole. That's the molar mass, which in this case is 55.8. Okay, so now I'm going to go through, make sure that all my units cancel. Moles of iron cancel moles of iron, moles of FeCl3 cancel with moles of FeCl3, grams of FeCl3 cancel with grams of FeCl3. Now I just multiply and divide as usual. 22 times 1 divided by 162 times 2 divided by 2 times 55.8 divided by 1 gets me 7.57 grams of iron. So I know I need a 7.57 gram sample of iron if, for whatever reason, I want to get 22 grams FeCl3 out.